Most real-world data is not centered at 0 with a standard deviation of 1. Pulse rates vary around 72 beats per minute. Test scores are distributed around a class average, not 0. So how do we still use the standard normal table? The solution is to convert everything to a z-score. Remember the z-score formula. Z is equal to x minus mu over sigma, where x is the observed value, mu is the mean, and sigma is the standard deviation. A z-score tells us how many standard deviations a value is from the mean. Once converted, we use the standard normal table to find probabilities, turning any normal distribution problem into a standard one. For instance, adult pulse rates are normally distributed with mean mu equals 72, that would be in beats per minute, and sigma equals 8 beats per minute. We want to find a probability that a randomly selected adult has a pulse rate less than 84 beats per minute. So if we draw a curve, adult pulse rates are normally distributed with mean 72, so right here in the middle, and standard deviation 8. So one standard deviation above the mean will be 80, and then 84 will be 1.5 standard deviation above the mean. We want to find a probability that a randomly selected adult has a pulse rate less than 84, meaning the area to the left of 84 on a normal curve. So the first thing we will do, we will convert that value of 84 to a z-score. So z will be equal to 84 minus 72, that is our mean, divided by 8, which is our standard deviation. So that will be 12 divided by 8, which is 1.5. So then we'll need to look up the z-table in order to find a probability that z is less than 1.5. If we look at our table, z 1.5 is here, 1.50. The probability is 0.9332. So the probability that a randomly selected adult has a pulse rate less than 84 beats per minute will be 0.9332. Or in other words, about 93.32% of adults have pulse rates below 84 beats per minute. In this next example, heights of adult men are normally distributed with a mean of 70 inches and standard deviation 3 inches. We want to find a probability that a randomly selected man is taller than 75 inches. Once again, we have a normal curve here. Our mean is in the middle of 70 and our standard deviation is 3 inches. In this case, we want to find the probability that a man is taller than 75 inches, meaning the area to the right of 75, and this is the area shaded here. So the first thing we'll need to do is convert that value of 75 to a z-score. Z will be equal to 75 minus 70, which is our mean, divided by 3, which is our standard deviation. That'll be 5 over 3, which is approximately 1.67. We round z-scores to 2 decimals. So we'll need to look up in our table the probability that z is less than 1.67. So if we find a value corresponding to the probability or the area corresponding to the left of a z-score of 1.67, that will be 0.9525. But remember, the table gives you cumulative area from the left, that is this area right here. So in order to find cumulative area on the right, we'll need to apply the complement rule and just do 1 minus 0.9525. Since we know that the total area under the curve is 1, we can just do 1 minus, and that will be 0.0475. In other words, approximately 4.75% of men are taller than 75 inches. In this last example, exam scores are normally distributed with a mean of mu equals 78 and sigma is 10. We want to find a probability that a student scores between 70 and 90. So I drew the curve here. Right here in the middle, we have our mean of 78. And the area shaded is the value of x equals 70 to the value of x equals 90. So we want to find the area under the curve from 70 to 90. In other words, the probability that a randomly selected student scores between 70 and 90. So here we'll need to convert both values into z-scores. For our first value of 70, we'll do 70 minus 78 divided by 10. That will give us a z-score of negative 0.8. For a second value of 90, 90 minus 78 divided by 10 will give us a z-score of 1.2. Now we'll need to look up in the table the probability that z is less than 1.2, which would be this area under the curve from the left of the 90. And then we'll look up the area to the left of negative 0.8, which will correspond to an exam score of 70, and that will be the area to the left of 70. So if we look at our table, the area to the left of negative 0.8 will be 0.2119, and the area to the left of 1.2 will be 0.8849. So in this case, we'll need to subtract the areas. So we'll do 0.8849 minus 0.2119, which will give us 0.6730. So in other words, the probability that a randomly selected student scores between 70 and 90 will be 0.6730, or about 67.3% of students scored between 70 and 90. So here's the three-step process. Normal distributions don't usually have a mean of 0 and a standard deviation of 1. So we can follow this process every time. Step number 1, convert the observed value to a z-score using the formula. Step number 2, look up the z-score in the standard normal table. And step number 3, read or calculate the probability, that is, use the complement or subtraction as needed. The z-score transforms any normal distribution into the standard normal distribution. That's why one z-table can solve thousands of different problems. Z-scores remove units and scale, making all distributions comparable. Heights, pulse rates, scores, salaries, all solved with the same approach. Thanks for watching. Please like and subscribe to keep learning with us. And don't forget, math success starts when you stay on the fast track.